right, thanks very much. Welcome to Stanford and this very interesting class. This is the first time I've gotten to hear some of the other folks in the energy at Stanford and SLAC area talk about what they're doing, so this has been really interesting for me. I'm Kroo. I work in the Aeronautics and Astronautics Department, which is just maybe 100 meters down the path here. By the way, if you are wandering around and have some time, this is a picture I took the other day from the hills above Stanford. So it's a lovely, lovely area to explore. So sustainable aviation is at the intersection of some of the work in energy and environment with aeronautics and astronautics. And so I'm going to tell you a little bit about some of the work that's going on. One of my graduate students, Jia Zhu, we'll talk just a little bit about some of the other things that are going on in the lab and in the department. Right, so in some sense, the efficiency of modern aircraft is pretty amazing. Here's a 737-800 flying from Seattle to Washington, D.C. It uses 3,700 gallons of gasoline, but it can carry 130 passengers. Actually, it can carry 162 passengers, but on average, it's about 80% full. And so that means 29 gallons are used by each passenger on the airplane, which translates to 81 passenger miles per gallon, which is not too bad. In fact, it also does this at 10 times the speed of automobiles. So this is pretty interesting. A typical car in the San Francisco Bay Area, actually, according to current statistics, carries about 1.3 passengers on average and gets about 25 miles per gallon right now, which is only 32 passenger miles per gallon. And in fact, this turns out to be pretty similar to typical load factors, that is the number of people traveling, converted to passenger miles per gallon on Amtrak. So airplanes do a tremendously good job of what they're supposed to do, transporting goods and people at high speeds. And they do it pretty efficiently. However, even though it gets high passenger miles per gallon, there are a lot of passenger miles in the world. And so there is a lot of fuel used. In fact, airplanes use something between 13 and 20% of the energy that's used for transportation, which translates roughly into that amount in terms of carbon emissions. And transportation uses something in the range of 13 to 20% of all of human-caused emissions. So that means that air transport's only 2 or 3%. It's not a dominant amount of carbon in terms of its percentage of human-caused sources. But it's interesting in that it deposits these emissions in very different places from cars and buildings. It deposits them actually in areas where the atmosphere is much more sensitive. And so it turns out to be pretty hard to predict the impact of depositing emissions at 30 to 40,000 feet. There's quite a bit of uncertainty involved in what the long-term effect is. But this is one of the research areas being pursued by folks in aeroastro and also in civil engineering here. Among other things, water vapor deposited at the right conditions creates contrails. The effect of contrails on climate is also very difficult to predict, but it may be even more significant than carbon dioxide emissions. Airplanes are interesting creatures and turn out to be a very significant source then of environmental impact. It may be one of the things that is most significant for you to be involved with. That is to say, one single round trip from here to Paris for you uses as much energy as the average as the average household in the building and appliances for the year. And so it's pretty hard to drive a car 100,000 miles in a year, but lots of people are frequent flyers flying 100,000 miles in airplanes. So, in addition to that, despite the economy, air traffic is growing tremendously, particularly in Asia and some developing countries. And so what we mean by sustainable aviation is to take the projected passenger mile, passenger kilometer demand, which is going up with time, that you see there in the blue line, the projected fuel use, which accounts for typical hoped for increases in airplane efficiency. And even with that, we're seeing tremendous increases in the impact on the environment. What we'd like to do is to maintain this kind of increase in capability without having a detrimental effect on the environment, and this would be sustainable. So research in the Astro department is proceeding on all kinds of things, doing more efficient routing of airplanes, managing the environmental footprint while increasing the capacity of the system, and thinking about ways to do this much, much more efficiently. Just as an interesting example, you might think about the fact that if contrails really do have an impact on the atmosphere that's detrimental, we could do things, for example, such as doing remote sensing to find out what conditions actually create contrails and just avoiding them, replanning in real time and avoiding those areas. Turns out that you only have to change the altitude by a few thousand feet to avoid the areas where the temperature and humidity is just right to form contrails. You can even think about combining real-time routing with social networks. So airplanes that start producing contrails talk to the other airplanes that then avoid them, and we evolve the air traffic routing system. I'm going to talk just a little bit about designing new airplanes to be environmentally compatible. So one way to do this is to increase engine efficiency. Turbofan engines are actually pretty efficient right now. They're about 40% efficient in converting the energy and the fuel to useful work in propelling the airplane. This is quite a bit higher than for automobiles, as you may hear from Professor Gerde's comments later. Electric propulsion can be 85% efficient. So there are interesting things that you can do there, but it's never going to be more than 100% efficient, and that means we can only get a factor of 2-ish out of this whole system. We should look at what's taking the energy in the first place. And when you think about it, if you take a weight and raise it up, you increase its potential energy, and the efficiency is how much energy you had to put into it to get it to change its energy state relative to how much potential energy it changed. So when you think about it, transportation is 0% efficient. We start with a certain kinetic and potential energy, right? Sea level at 0 speed. We go fly somewhere, we end up also with 0 potential energy at 0 speed at the end. And so we're using all this energy for just to move you, which in theory takes no energy. So why does it take energy? It's really just a matter of distance times force, and that force is drag. So to aerodynamicists, our goal is to reduce the drag. And one way to think about this when airplanes are flying along, the weight of the airplane is supported by the lift, and the drag then is the weight divided by the ratio of lift to drag. Ratio of lift to drag is a parameter, sometimes called L over D. It's a parameter that aerodynamicists like to use because it's dimensionless and has some interesting physical interpretations. So lift to drag ratios of airplanes can be and are considerably greater than 1. so that we can lift a 100,000-pound airplane with much less thrust than 100,000 pounds. And in fact, the lift-to-drag ratio of an airplane can be thought about as the distance an airplane would glide forward compared to the distance it sinks downward if it were gliding. So if we just build a model airplane here, and try to give you an idea of paper airplane lift-to-drag ratios. Here is here's one thing we can do. So that was about 4-to-1, 4 times as much lift as drag, because the lift-to-drag ratio also, if you work out the free body diagrams, the distance flown forward compared to the distance down. Well, you can do the same for cars. The lift is generated by the wheels on the ground. And you can look up the rolling resistance of tires, the friction coefficient, which is 1 over that ratio, the normal force and the drag force. So the rolling resistance of cars, typical BMW 5 Series tires, is about 100-to-1. The friction coefficient is about 0.01. But that's at 0 speed. At 60 miles an hour, you add the aerodynamic drag. The ratio of lift to drag is about 40-to-1. And at 120 miles per hour, it's about 16. High-speed rail, steel wheels on steel rails, is about 1,000 at 0 speed, but rapidly falls also with speed. A 550-foot destroyer at 35 knots is about 18. And here are plots of airplanes. Given that this lift-to-drag ratio is like the fundamental reason we need energy, you would think that airplane lift-to-drag ratio would have improved a great deal from 1960 and the 707. But in fact, even the 787 is in the range of 20 or so. The point is that in all this time, we haven't done anything. Well, that's not really true. In fact, the cost of flying has gone down in real terms by a factor of about 3. So the problem with this is that it's not just about aerodynamics. It's fundamentally driven by cost. And we could do things to dramatically improve the efficiency, reduce the energy use of airplanes if there were sufficient incentives. In fact, here's a sailplane with a lift-to-drag ratio of 70-to-1. It's a record-holding lift-to-drag ratio for an airplane. But the trick is to manage the combination of cost and performance in terms of utility as well as environmental performance. So one of the things my students have done recently is to explicitly include environmental metrics in the overall design of airplanes. And what you see here is a measure in particular of an estimate of the 100-year global warming associated with a fleet of airplanes of a particular type compared to the cost. Each of these is an optimization problem. So this is a Pareto front. Every point here, no point on here at a given cost has a better environmental performance, but it's a trade. So along this front, we have things with lowest cost on the left, lowest environmental impact below. And the interesting thing that you see here is that the curve is not some simple straight line. In fact, you can, for a very small amount of cost increase, dramatically reduce the impact on, in this case, on climate. So we're looking at things to do there. One of the reasons that airplanes generate drag is because they move the air around as they go by. This is a picture of an airplane flying above a cloud, and you see the vortex formation there. One thing we could do is fly airplanes in formation. Some of my students are looking at how you might use autonomous systems to automatically have them fly together. And in fact, DoD is looking at this now too, and there is actually a program to fly a number of C-17s together. And Airbus is funding some students such as Jia to look at how this could be applied to commercial aircraft. We could look at really different things, next generation engines, laminar flow, new configurations. This is a study that Boeing did with electric airplanes for 70% fuel burn reduction if you could have really, really good batteries. Electric propulsion is really interesting. Here is a Chinese design that recently flew. Here's a design done by a company in Santa Cruz thinking about how we could really change things by thinking about personal electric transportation. So, Stanford Research, Sustainable Aviation, provides a framework for integrating together a lot of different things that are going on in aero research. It's a vital field of study for future students, and it really provides a focus on one of the most important problems in aviation today. So with that,